The 3-slot payphone part 2 is the second of 2 videos about this type of payphone. In part 2 you'll get a thorough tour of the mechanical and electromechanical parts inside the payphone and learn exactly how the payphone functioned. The separate part 1 video provides a user's perspective of making local and long-distance payphone calls. Okay, so now we're going to go inside the payphone to see exactly how it works. Before we do that, I want to clarify some terms that I use frequently throughout this part. You're looking at the front of the payphone, and this is the rear, or backplate. Some parts have 2 sides that are quite different, and we examine each side separately. The front side, or face, of any such part is the one pointing towards the front of the payphone. The back or rear side, or face, is the one pointing towards the backplate. Also, some parts move. When I refer to the motion of a part as being forward, it is moving towards the front of the payphone. When I refer to the motion of a part as being backward, it is moving towards the backplate. Try to remember this as we are looking at parts from the front, the rear, and even sometimes the side profile. We are going to begin with the coin chute assembly. This is the front face of the coin chute assembly. It has 3 chutes or channels, one for each coin denomination. Here is the nickel channel, the dime channel, and the quarter channel. The coin chutes are made of stainless steel. At the bottom of the assembly, the chutes converge so that emerging coins will be lined up to drop into the hopper. This is the rear face of the coin chute assembly. In addition to the 3 channels, there are 2 gongs. This is the cathedral gong, and this is the solid gong. Also up near the top is this electromagnet, which is used for nickel operation. Let's watch how the coins flow through their chutes. For each coin, we'll look at the front face at regular speed, then in slow motion, and then the rear face in regular speed, and then in slow motion. We'll start with the quarter. And now the dime. And the nickel. When coins emerge from the bottom of the coin chute, as you see here, they drop directly into this bin, which is called a hopper, and we'll be looking at this in detail a little later in the video. There is one other chute to consider, and that is the coin return chute. This chute is a wide sheet metal down-sloped catch-all for rejected deposits. Some deposits are rejected by the coin chutes, such as nickels and dimes deposited in the wrong slots, or foreign coins, slugs, and tokens that are too small. Here are some other circumstances in which deposits fall into the coin return chute. Washers rejected by the washer reject mechanism. First nickels deposited with the handset on hook. Held first nickels if an off-hook handset is returned to on hook. Held first nickels if the coin release push button is pushed. And finally, any rejected discs that are stuck near the top of the coin chute assembly if the coin release push button is pushed. Return chute discs slide down the chute and drop into the coin return bucket. When the upper housing is mounted in its in-service position, the opening to the coin return bucket lies directly below the bottom of the coin return chute. Now let's take a look at the two types of gongs. This is the solid gong. It gets struck by both nickels and dimes. A nickel passing through its chute will strike the gong once at its lower edge. A dime passing through its chute will strike the gong twice, once on its upper edge and once on its lower edge. Let's look at the nickel and dime gong interaction in slow motion. First the nickel and then the dime. This coiled gong is made of spring-tensioned hardened steel. For over 200 years, clockmakers have made use of coiled gongs inside their clocks. Sometimes the chimes produced by these gongs were meant to mimic the chimes of churches or cathedrals. Because of this, the term cathedral gong came into general usage. Let's watch the quarter interaction with the gong in slow motion. Associated with each gong is a signal transmitter or microphone. One is mounted inside the solid gong, the other is located in close proximity to the cathedral gong. Each signal transmitter picks up the sounds made by its gong and sends them over the voice transmission path to the toll switchboard operator, who uses these sounds to identify the amount of money being deposited. The two signal transmitters are wired in parallel with a 22 ohm resistor, which controls the volume level and protects the transmitter against excessive current. You can't actually see the resistor since it's hidden behind this black spacer mounting plate. However, its connection points are these two terminals. Taking the handset off hook and replacing the handset on hook causes the Switchhook assembly to pivot on its axis. Going off hook closes these two sets of switchhook contacts, which provides a closed direct current loop path through the payphone. Also a part of the switchhook assembly is this operating arm. When the handset is on hook, the operating arm projection is tilted to a downwards angle as you see here. When the handset goes off hook, the operating arm projection tilts upwards to this horizontal position. The operating arm controls the opening and closing of this hinged gate, which is mounted on the chute assembly. The gate has an attached lever that protrudes through an opening in the coin chute assembly. The gate lever has an upper and lower roller located at the end of the lever arm. The position of the lever is such that the top of its upper roller comes into contact with the underside of the operating arm. Here, my red probe represents the operating arm. When the handset goes on hook, the operating arm tilts downwards, which forces the gate lever to swing down, which opens the gate. When the handset goes off hook, the operating arm raises upwards, taking pressure off the gate lever. The gate lever swings up, because the gate closes under the tension of its hinged spring. When the gate is open, part of the gate protrudes into the 25-cent chute. Here, a quarter is deposited with the handset on hook and the gate open. Notice that its progress is stopped by the gate protrusion. When the handset goes off hook, the gate closes, removing the protrusion from the 25-cent chute, allowing the quarter to continue on its path to the cathedral gong and then to the hopper. If a quarter is deposited when the handset is off the hook, the gate is closed and the quarter flows all the way through its chute unimpeded. We'll take a look now at all the peculiarities associated with the depositing of nickels. If the first nickel is deposited with the handset on hook, the gate is open. The nickel will travel down the 5-cent chute to the gate area and fall out of the open gate into the return chute, and then down to the coin return bucket. If the first nickel is deposited with the handset off hook, the gate is closed. The nickel drops to the same area as before, but is prevented from falling out by the closed gate. Just above the gate, the 5-cent chute widens into two side-by-side coin paths. This arrow points to the left path, and this arrow points to the right path, which is hidden by the gate. The path to the right provides an unimpeded drop past the gate area. However, a nickel must be deflected in order to take this path. Due to the angle of the 5-cent chute, the path to the left is the natural path automatically taken by the first deposited nickel. This path leads to a holding latch located in the gate area. The holding latch captures and retains the nickel. The holding latch has a tab on its lower edge that the bottom of the nickel rests on. The nickel is prevented from falling out by the closed gate. The holding latch has an upper hinge on which it can swing freely unless it is locked. The locking latch is a spring-loaded pivotable latch. In its normal position, it prevents the holding latch from pivoting by a catch arrangement. The locking latch can be tripped so that its catch on the holding latch rotates upwards, away from the holding latch. When this occurs, the holding latch is free to pivot. The locking latch is tripped by the deflection of its lower tab, which is located in the right side nickel channel just below the gate. The locking latch is tripped by the deposit of the second nickel. The second nickel travels down the 5-cent chute towards the holding latch, where it strikes the edge of the first nickel. This deflects the second nickel back to the right side of the widened 5-cent chute. It soon encounters the bottom tab of the locking latch, which is struck with sufficient force to trip it. With the holding latch unlocked, the weight of the first nickel resting on its tab causes the latch to pivot backwards, which releases the nickel. The first nickel now drops down the left side of the 5-cent chute, parallel to but slightly behind the second nickel on the right side. Not far below the gate area, the 5-cent chute narrows back down to a single coin width and slopes down to the right and then sharply zigzags to the left. The two nickels proceed in line along this chute with the second nickel in the lead. They both strike the lower edge of the gong and then drop into the hopper. An electromagnet is mounted on the top left side of the rear face of the coin chute assembly. The purpose of this electromagnet is to provide a means for the payphone to accept the deposits of single nickels. This is necessary to allow the calling party at the payphone to deposit the correct amount for the toll charges on a long-distance call, which may require a single nickel as part of the charges. The winding of the electromagnet forms part of the loop circuit through the payphone. As soon as dial tone is received on originating calls, or as soon as the payphone is answered on incoming calls, the electromagnet is energized and its armature operates. When operated, an arm attached to the armature projects into the 5-cent chute. This arm blocks the nickel's pathway to the holding latch, causing it to deflect away and continue dropping down the 5-cent chute. Let's follow the path of a nickel when the electromagnet is energized. The nickel will first appear where the red arrow is pointing. It will strike the electromagnet's armature extension, which is protruding into the nickel channel. This deflects the nickel away from the holding latch, and it drops down the wide part of the 5-cent chute past the gate area. It then resumes its normal path along the 5-cent chute, zigzags, strikes the lower edge of the gong, and drops into the hopper. The electromagnet forms part of the voice transmission path. To minimize the effect on transmission quality, a capacitor is placed in parallel with the electromagnet. The capacitor can be seen here, located beneath the coin return chute. There is also a resistor in series with this capacitor that protects the dial-off normal contacts from excessive arcing. The resistor is located here, near the bottom of the rear face of the coin chute assembly. We're going to take a look now at the activities that occur inside the upper housing when the coin release button is pushed. First, we need to understand how the coin chute assembly is mounted in the upper housing. Here we're looking at the front face of the unmounted coin chute assembly. It has 3 mounting holes. 2 are near the top, 1 at each side, and 1 is near the bottom on the right-hand side. The top holes are not threaded, and 2 very long screws pass through these holes. This holds the coin chute in a relatively fixed position as far as up and down or side-to-side motion is concerned, but does not prevent the coin chute from moving backwards and forwards. The bottom hole contains a rubber grommet, and a mounting screw also is passed through this hole. The 3 mounting screws screw into threaded holes on brackets attached to the upper housing. The 2 upper screws are long, but have short threaded ends and so do not tighten down against the coin chute assembly. This permits back and forth motion of the upper part of the coin chute assembly. 2 coil springs fit over the shaft of these screws. The spring tension restrains the motion of the coin chute assembly, which rests in its most forward position against the screw mounting brackets. The bottom screw is short and tightens down against the rubber grommet. However, the rubber grommet itself permits a small amount of back and forth motion of the coin chute assembly. This mounting arrangement results in a coin chute assembly that can be tilted backwards against the tension of the springs, which will compress if acted upon by an external force. The external force needed to tilt the coin chute assembly backwards is applied by pushing the coin release button. The coin release button presses against this hinged lever inside the upper housing. The lever swings backwards, and this projecting arm in the middle of the lever pushes against the coin chute assembly, tilting it backwards. As the coin chute assembly moves backwards, the right side roller on the gate operating arm engages this stop bracket and begins to roll down the face of this bracket, causing the operating arm to tilt downwards. This opens the gate. The back-tilted coin chute assembly and the open gate help release any kind of stuck discs in that area and send them down to the coin return chute. The open gate also releases any kind of discs being held in the nickel holding latch. Let's now take a look at how electrical continuity is provided between the upper housing and the backplate and lower housing. The upper housing can be removed from the payphone without having to perform any wiring disconnections. This is because electrical conductivity between the circuitry in the upper housing and circuitry on the backplate and lower housing is provided by a set of 5 flat transfer contacts mounted on the backplate and a set of 5 spur contacts mounted on the upper housing. Here are the 5 transfer contacts mounted on the backplate. Here are the 5 spur contacts mounted inside the upper housing. The transfer contacts are spring tensioned. When the upper housing is placed into its in-service locked position, the spur contacts mate up with and apply pressure to the transfer contacts, causing them to deflect. This pressure ensures that good electrical conductivity is maintained between the spur and transfer contacts. This arrangement completes the electrical paths for the circuits within the payphone. Let's turn our attention now to the washer reject mechanism. The washer reject mechanism is located inside the upper housing at the top, immediately below the coin gauge. The mechanism contains 3 wheels, 1 for each coin slot. Each wheel consists of 2 spokes and a weighted tab that hangs vertically from the bottom of the wheel. When a coin is deposited, it strikes the lower spoke of its wheel, causing the wheel to rotate downwards. As the coin continues to move, the higher spoke strikes the back face of the coin, deflecting it at an angle that lines it up with its coin chute, which it now enters and begins its travel down to the hopper. As soon as a coin has fallen beyond its washer reject mechanism area, its wheel rotates back upwards under force of gravity on its weighted tab. This brings the wheel back to its normal rest position, with the weighted tab hanging vertically from the bottom of the wheel. When a washer is placed into a coin gauge slot, it also strikes its wheel's lower spoke and starts the wheel turning downwards. As the washer continues to drop, the upper spoke rotates downwards, but instead of striking the back face of the washer, it simply enters the hole in the washer. Because of this, the washer is not deflected towards a coin chute, but instead just drops vertically downwards under the force of gravity to the coin return chute and into the coin return bucket. Here's a cutaway side view of a payphone, showing the 2 different paths taken by coins and washers. We're going to turn our attention now to this section of the payphone. This is the apparatus that controls the final disposition of the coins, that is, whether they are to be collected or returned. Here are the parts that can be seen from the front view. First we have the hopper, which is a bin that holds the coins pending their final disposition, and to which other coin disposition apparatus is mounted. Next is the steel tray that provides the mounting base for the hopper. And finally we have the coin relay winding and its armature. It is the energizing of the coin relay that initiates all the activities required for coin disposition. In addition to the apparatus shown here, there are several other parts we will be looking at. These include the trigger contacts, the trap lever, the selector card, the cam, and the vane. We're going to take a look at the payphone schematic diagram so we can see the electrical effects of the coin disposition circuitry. This schematic of the payphone depicts its idle on-hook state. Here are some of the parts that we've already looked at or will soon be looking at. Here are the tip and ring leads that connect the payphone to the central office. Here are the 2 sets of switchhook contacts. Here's the dial pulse contacts and the hopper trigger dial shorting contacts. These are the signal transmitters that send the gong signals to the operator. And this is the electromagnet that provides for single nickel deposits. Here's the voice transmitter and the receiver. Here's the payphone local ground supply, the hopper trigger mate contacts, the coin relay assembly R1 resistor, the coin relay winding, and the coin relay brake mate contact set. We know that taking the handset off the hook closes the switchhook contacts. On the schematic it looks like this. Nothing else happens in the payphone until a coin is deposited. Let's begin with the hopper. In this view we are looking down through the top opening of the hopper. The coin relay assembly has been removed for clarity. The hopper is made from a die-cast zinc alloy and it mounts to the steel base. It is designed to hold up to about 20 mixed coins. The exit point for all 3 coin chutes lies directly above the hopper opening, so all coins exiting their chutes fall into the hopper. The first item encountered by a coin entering the hopper is this yellow-colored nylon trigger. The trigger is mounted on the coin relay assembly and it extends inside the hopper through a front opening. In its normal release position, The trigger lies horizontally inside the hopper shaft, about 5/8 of an inch from the top. When a coin strikes the trigger, it trips it to its operated position, which is tilted downwards from the horizontal. The trigger controls two sets of contacts, which are this set of break contacts and this set of make contacts. When the trigger is tripped, the break contacts open and the make contacts close. The tip of this spring lever holds the trigger in its tilted off-normal position. On the schematic, that change looks like this. The purpose of the dial shorting contacts is to prevent dialing from occurring when dial tone has been obtained by fraudulent means, in which no coins have been deposited. When the circuit is in this state, it causes the line relay in the central office to operate. The red line shows the circuit path. From payphone ground, through the closed hopper trigger contacts, through the coin relay winding, through the transmitter, through the electromagnet, through the signal transmitters, through the closed dial pulse contacts, through the closed switchhook contact, out on the ring lead, through the central office line relay winding to central office negative 48 volt battery. There is more than one current flow path from terminal T to terminal RR. I have just shown one of them for simplicity. Notice that no current flows along the tip side of the line to the central office. This is because at this point in time, the tip side of the line is open at the central office. Operating the line relay by using a local ground at the payphone is known as the ground start method. The resistance of the ground return path to the central office is generally less than 50 ohms. As we saw earlier, the operation of the line relay initiates a sequence of events that results in the provision of dial tone to the payphone caller. Once the caller has dial tone, dialing can commence, since the trigger dial shorting contacts are open. So let's suppose a local number is dialed, a conversation is held, and then the payphone user hangs up. This reopens the switchhook contacts, and the state of the payphone circuit schematic looks like this. At this time, the coin trunk circuit between the line finder and the first selector maintains the connection through the line finder to the payphone. The coin trunk has already sensed that the call was answered and has set itself to collect the coins. When it senses that the payphone user has replaced the handset on the switch hook, it connects the coin collect voltage to the tip and ring of the payphone line. However, the high voltage current only flows over the tip side of the line, since the ring side of the line is open at the switch hook contact. The red line indicates the circuit path for the high voltage current, which flows through the coin relay winding to the local payphone ground. This operates the coin relay. This diagram depicts a situation in which both the tip and ring conductors are used for carrying the high voltage coin relay operating current. This method can be used for payphones which are beyond the distance range for effective operation of the coin relay using only the tip conductor. For these payphones, a Type 685B subscriber set is substituted for the Type 685A subscriber set. The difference is that the 685B subset has a relay designated as the S36 relay that is placed in series with the coin relay operating path. When the high voltage is applied, the S36 relay operates. Its make contact bridges the tip and ring leads together, allowing the high voltage current to flow over both the tip and ring conductors. This cuts in half the resistance of the operating path between the central office and the payphone. Another situation in which both the tip and ring conductors may be used is on long-distance calls. This occurs when the operator tries to collect or return coins while the payphone customer is still on the line. In these situations, the ring lead is not open since the switch-hook contacts are closed and there is a DC path through the payphone loop. This is the coin relay, which is fast to operate and slow to release. The purpose of the coin relay is, when operating, to physically cause the actions necessary for coin collection or return. This includes the release of the coin trap and the tilting of the vane. In addition, when operating, the coin relay resets the trigger to its horizontal position, recloses the dial shorting contacts, and operates its own break-make contact set. The purpose of the coin relay when releasing is to reset the coin trap to its horizontally locked position and to reset the vane to its vertical position. In addition, when releasing, the coin relay opens the trigger make contacts and releases its own break-make contact set. The coin relay is operated by a short, say about 1/4 of a second, pulse of high voltage direct current from the central office. The timing as to when this pulse is to be applied is determined automatically by central office trunk equipment or manually by an operator. Positive coin collect battery or negative coin return battery, nominally 110 to 125 volts, is applied to the tip and ring leads of the payphone line. The ground return path is supplied at the payphone via the operated make contacts of the hopper trigger. First, let's see what happens at the upper end of the coin relay assembly when the coin relay operates. Here's a view of the top end of the coin relay assembly as it would appear immediately prior to the operation of the coin relay. This is the trigger brake contacts, the trigger make contacts, the coin relay brake make contact set, the top of the armature with its release timing adjusting screw, the release timing spring, and the switch card. Now we'll zoom in for a close-up. The trigger is in its tripped position. The trigger dial shorting contacts are open. The trigger make contacts are closed. The coin relay contact set is in its released position with the brake contacts closed and the make contacts open. The armature is in its release position away from the relay core. This is the switch card. It's made of fennel fiber and is loosely horizontally mounted so that it has the capability of sliding backwards and forwards. It contains a series of notches and slots that are in contact with the movable contact springs, such that when it slides backwards and forwards, these contact springs move with it. When the armature operates, it engages the front edge of the switch card, forcing it backwards, which changes the positions of the contact springs. This is the release timing spring. It is a spring tension plate that is anchored at its bottom edge. This allows the upper part to tilt backwards under pressure of this screw on the armature. When the armature closes, the end of the screw engages the spring plate, tilting it backwards. The amount of tilt can be adjusted by turning the screw clockwise for more tilt, anti-clockwise for less tilt. The larger the tilt, the higher the pressure the spring puts on the armature. The screw adjustment affects the release time of the relay. One other thing to note is the position of this lever spring. It's holding the trigger in its operated position. When the armature operates, the switch card will push this lever backwards, away from the trigger support surface, allowing the trigger to tilt back to its horizontal position under the tension of its return spring. Let's watch the armature operate in slow motion. Now the trigger dial shorting contacts have changed from open to closed. The trigger make contacts are still closed, although in this view they are hidden behind the support bracket. The lever spring has been pushed backwards, allowing the trigger to reset to its horizontal position. The contact set of the coin relay has changed from closed brake contacts and open make contacts to open brake contacts and closed make contacts. And lastly, the release timing spring has tilted backwards under pressure from the adjusting screw. Looking at the schematic for this point in time, we see the trigger dial shorting contacts are closed. The trigger make contacts are still closed. The coin relay contact set has operated, with the brake contacts now open and the make contacts closed. The purpose of the coin relay contact change is to initiate the release sequence of the coin relay. Once the armature has fully operated, it no longer requires the high voltage operating current. The coin relay's closed make contacts short-circuit the coin relay winding. Its magnetic field begins to collapse. However, this collapsing field induces a current to flow through the short circuit, such that an opposing magnetic field is established that slows down the overall collapse. This effect is known as Lenz's law. In addition, the relay's magnetic gaps have a large surface area, and the air gap itself is very thin. As such, the armature remains in its operated position until the current flow is only a small fraction of the minimum operating current, which is 48 milliamperes. The release time is nominally set to 0.6 seconds, which provides ample time for a fully stacked hopper load to clear through the trap. The coin relay release sequence is initiated very quickly, and it is necessary to keep the 110 volt to ground path intact for a longer period than the start of the release sequence. This is to ensure that all coin supervisory functions in any of the trunks involved on a coin call have sufficient time to complete the function that utilizes the ground from the payphone. On a long distance call, a red coin pilot lamp on the bottom part of the switchboard face lights up when the operator operates the coin collect/return key, and the ground path at the payphone closes through to the central office trunk. This just indicates to the operator that the coin collect return function is actually being performed. Keeping this ground path closed after the coin relay winding has been short-circuited ensures that the lamp is lit for an adequate interval, which is about 1/4 of a second. The resistor substitute is required to prevent a surge in current when the coin relay winding is short-circuited. Without the resistor, the current would more than double. The resistance lamps in the CO trunk would absorb this excess current. However, continual use in this way would greatly shorten the life of these lamps, necessitating frequent replacement. And finally, the resistor helps prevent the severe arcing that would occur when the trigger make contacts open, when the armature begins releasing. Now let's look at the mechanics of the coin disposition that occurs in the hopper in relation to the operation of the coin relay. We've already examined the trigger, which is the first item encountered by a coin entering the hopper. Now we'll look at the second item, which is this yellow-colored nylon trap door, which lies about 2 1/4 inches down the hopper shaft. At this time, the trap is locked in its horizontal position, allowing deposited coins to stack up on top of it. When the time comes for coin disposition, the trap is unlocked and it flips down, allowing the stacked coins to fall downwards deeper into the hopper shaft towards their final destination. At the bottom of the hopper, there is a nylon flap called a vane, which is hinged at its lower edge. The vane can pivot on its hinge. It has 3 positions. In its normal rest position, it sits straight up, that is, at 90 degrees to the base, and would present its top edge to the center line of the shaft opening. It can be tilted 40 degrees to the right, as you see here, or 40 degrees to the left, as you see here. When the vane is tilted to the right, it blocks off the passageway to the cash box and opens up the passageway to the return chute. When the vane is tilted to the left, it blocks off the passageway to the return chute and opens up the passageway to the cash box. The vane has a horizontal stem that protrudes out of an arc-shaped slot on the front of the hopper. This stem can be used to flip the vane from side to side. The motions of the vane are controlled by this selector card cam acting on the vane stem. Let's see what happens when I drop a coin into the hopper with the vane tilted to the right. Notice that the coin was deflected to the left towards the coin return chute. Now let's see what happens when I drop a coin into the hopper with the vane tilted to the left. Notice that the coin was deflected to the right towards the cash box opening. So, with a stack of coins in the hopper and the vane tilted to the right, when I release the trap, the coins drop into the coin return bucket. And with a stack of coins in the hopper and the vane tilted to the left, when I release the trap, the coins drop into the vault. Normally the cash box would be in the vault, but I removed it for clarity. Let's see how the trap locks and unlocks. The yellow trap pivots on a hinge located on the outside front of the hopper. Just below the trap hinge is a stainless steel trap lever. This lever is also hinged along its bottom edge, which allows the lever to pivot. Both hinges are served by a folded hinge pin. When the trap lever tilts backwards, its top edge forces the trap to pivot upwards to its horizontal position. As long as the trap lever remains tilted back, it supports the trap, holding it locked in its horizontal position. When the trap lever is tilted forward, the trap is no longer supported and it swivels down to its vertical position. The motions of the trap lever are controlled by this selector card acting on the projecting tab at the bottom of the trap lever. Now we'll examine exactly how the operation of the coin relay controls the motions of the vane and the trap. This is the rear view of the lower part of the coin relay assembly. You can see the coin relay winding in the background. Here are the major parts. This is the coin relay coil pull piece extension. This is the armature restoral spring. This is the armature rocker arm. This is the selector card. This is the slot in the selector card for the trap lever tab. This is the cam, and this is the slot in the cam for the vane stem. The yellow colored nylon selector card hangs from this tab on the rocker arm. Here's a side view of the rocker arm. It's attached to the lower part of the armature. When the armature operates, the rocker arm tilts downwards, and when the armature releases, the rocker arm tilts back upwards. Since the selector card hangs from a tab on the rocker arm, it moves vertically downwards and upwards, along with the tilting of the rocker arm. On the far side of the rocker arm, we can see the armature restoral spring. It stretches and tensions up when the armature operates. This provides the power to restore the armature to its normal rest position when the relay winding is de-energized and the magnetic flux fades to a point where it's overcome by the tension of the spring. Let's watch the action of the armature, the rocker arm, the selector card, and the restoral spring. Embedded in the selector card and lying horizontally near its top edge is this permanent bar magnet. As viewed from the rear, its south pole is on the left end and its north pole is on the right end. This pole piece extension is connected to the upper end of the relay core, so when the relay winding is energized, the pole piece becomes magnetized and takes on the magnetic polarity of the upper end of the relay core. When positive coin collect voltage is applied across the coin relay winding, the top of the winding is magnetized as a north pole, which extends to the two tabs on the pole piece extension. When negative coin return voltage is applied across the coin relay winding, the top of the winding is magnetized as a south pole, which then extends to the two tabs on the pole piece extension. The fit between the selector card slot and the rocker arm tab is loose so that the selector card has some lateral and vertical wiggle room. When the coin relay coil is energized for coin collection, Its upper end has a north magnetic pole. The south pole end of the permanent magnet in the selector card is attracted to the north pole of the pole piece extension tab, located just above it. And the north pole end of the permanent magnet is repulsed by the north pole of the pole piece extension tab, located just above it. Looking at the rear face, this causes the selector card to tilt slightly to the right, as can be seen here. The left side gap has narrowed, while the right side gap has widened. Let's watch the action of the selector card as the coin relay is energized for coin collection and its armature operates. Notice the effect that the downward motion of the right tilted selector card had on the cam. The slight angle of engagement between the selector card and the stem on the cam caused the cam to deflect to the right. When the coin relay coil is energized for coin return, its upper end has a south magnetic pole. The north pole end of the permanent magnet is attracted to the south pole of the pole piece extension tab, located just above it. And the south pole end of the permanent magnet is repulsed by the south pole of the pole piece extension tab, located just above it. Looking at the rear face, this causes the selector card to tilt slightly to the left, as can be seen here. The left side gap has widened, while the right side gap has narrowed. Let's watch the action of the selector card as the coin relay is energized for coin return and its armature operates. Notice that the downward motion of the left tilted selector card engaged the stem on the cam, and the angle of engagement caused the cam to deflect to the left. The purpose of the cam is to tilt the vane in the appropriate direction for coin collect or coin return. The pivoting motion of the cam causes the vane to pivot along with it. This is because when the coin relay assembly is mounted to the hopper, this stem on the vane resides inside this slot on the cam. When the coin relay operates, the selector card performs one other important task, and that is the forward tilting of the trap lever. When the selector card moves downward, it engages the tab on the bottom of the trap lever, causing it to pivot downwards, in much the same manner as my red probe is doing here. The trap lever tilts forward, releasing the trap, allowing the coins to drop through. This occurs because when the coin relay assembly is mounted to the hopper, this trap lever tab resides inside this slot in the selector card. When the coin relay is not operated, the trap lever tab rests on the bottom edge of this slot. There is a considerable gap between the top face of the tab and the top edge of the slot. This requires the selector card to move downward some distance before the top edge of its slot engages the trap lever tab. This travel distance allows the cam to fully tilt before the trap lever starts to pivot. This ensures that the vane is set in its tilted position before any coins start to drop. This completes the demonstration of all the activities associated with the operation of the coin relay. As we saw earlier, as soon as the relay has fully operated, its release sequence is initiated by the short circuit across its winding. Let's now take a look at what happens as the relay's armature begins to release. We'll begin here with the armature fully operated. The armature starts to release when the residual magnetism holding it to the relay core has diminished sufficiently to be overcome by the tension of the restoral spring and the pressure of the release timing spring. As the armature starts to return to its normal position, the switch card begins moving forward due to the tension of the contact springs. This allows the end of the lever spring to re-engage with its stop on the already released trigger. This stops the forward motion of the lever spring, which in turn stops the forward motion of the dial shorting spring. This maintains the dial shorting contacts in their closed position.
Notice that the forward movement of the armature has also permitted the release timing spring to restore to its normal position. With the lever spring held fixed, as the switch card continues to move forward, the trigger make contacts open. This cuts off the payphone ground supply and stops the flow of high voltage current from the central office, if it is still being applied. Notice that the coin relay contact set is still operated, maintaining the short circuit around the relay coil. Removing the ground supply before removing the short circuit prevents the coin relay from reoperating if the high voltage from the CO is still being applied. As the switch card and armature continue to move forward, the coin relay contact set restores to its normal position, removing the short circuit around the relay coil and restoring the short circuit around the coin relay resistor. The rocker arm pivots back to its normal position as the armature releases. The rocker arm moves the selector card vertically upwards to its normal position. The upward movement of the selector card also moves the cam back to its normal position. Because the vane stem resides inside the cam slot, the movement of the cam restores the vane to its upright neutral position. Because the coin trap lever tab resides inside this selector card slot, the upward movement of the selector card tilts the tab upwards. This in turn tilts the trap lever backwards, forcing the trap back to its horizontal position, locked there by the support of the trap lever. Now we're going to take a detailed look at the vault and cash box. When I insert the key into the vault door lock and turn it to the right as far as it can go, the vault door can simply be pulled away from the lower housing. Inside the vault, we can see the front face of the cash box. Each cash box has its own unique identity number. A wire handle on the cash box can be flipped up so that the cash box can be pulled out of the vault. The cash boxes were removed and replaced with empty ones on a regular basis by telephone company personnel called coin collectors. Strict control of the vault keys was maintained. Coin collectors were given the keys to the payphones on their route for the day at the start of their shift and had to be returned at the end of their shift. You'll notice that the cash box is equipped with a lid, the main purpose of which is to prevent the coin collectors from pilfering the telephone company's hard-earned cash. You may be wondering how coins drop into the cash box, since there doesn't seem to be any opening in the lid. The lid has a sliding shutter, which is controlled by this shutter lever. When a shutter is first opened by moving its lever all the way forward, as you see here, and then closed by moving its lever all the way to the rear, as you see here, the shutter and its lever become locked in the closed position. The only way the shutter can be unlocked is by resetting its locking mechanism, which we'll be looking at shortly. The opening of the shutter is accomplished automatically by the insertion of the cash box into the vault. The closing and locking of the shutter is accomplished automatically by the removal of the cash box from the vault. These actions are controlled by the coin receptacle rail, which is mounted to the ceiling of the vault. A short slot near the front of the rail, shown here by the red arrow, provides space for the insertion of the tip of the shutter lever. When the cash box is being inserted into the vault, the part of the shutter lever in the slot catches against the rail when it reaches the back end of the slot and is held in a fixed position as the cash box moves backwards. When the cash box is fully inserted, the shutter lever is in its foremost position and the shutter is fully open. When the cash box is being removed from the vault, the part of the shutter lever in the slot catches against the rail when it reaches the front end of the slot and is held in a fixed position as the cash box moves forward. Before the cash box is fully out of the vault, the lever reaches its rearmost position and the shutter is fully closed and locked. Due to the arc-shaped motion of the lever, it has at this point receded clear of the rail stop, so the cash box can be fully removed. Notice that there is a locking mechanism securing the lid to the cash box. The front of the lid has a vertical hasp and the front of the cash box has a staple. The slot of the hasp fits over the staple. A ring seal can be inserted through the eye of the staple. That looks like this. It prevents lifting the hasp away from the staple and opening the cash box. After coin collectors return full cash boxes to the telephone company, the seals are broken, the cash box is emptied, and then new seals are installed on the empty cash boxes, ready for replacement back in the payphones. These seals are easily broken, but any coin collector returning a cash box with a broken seal would be in serious trouble. With the ring seal removed, the cash box can be opened. The first step is to tilt the hasp away from the staple. Then the lid can simply be tilted upwards. A cash box has the capacity to hold about $40 worth of a typical mix of nickels, dimes, and quarters. When the lid is turned upside down, the shutter locking mechanism is exposed. About a 1/4 clockwise turn with a slotted screwdriver resets the lock. With the shutter lock reset, the lid can be remounted onto the cash box, and the cash box reinserted into the vault. There is one other item to look at in the vault area, and that is this booster spring mounted to the floor of the vault. It minimizes the clearance between the cash box lid and the rail, preventing coins from bouncing onto the lid. This concludes my Part 2 video on the 3-slot payphone. You can find the Part 1 video and any other of my phone videos by searching for my channel name, Hicken65, on YouTube. As always, if you have any questions, please put them in the comments area of this YouTube video, and I will attempt to answer them. Thanks for watching.